Uh, okay, good evening, everybody. Good evening, and thanks for joining us. My name is Scott Lytle. I'm the chapter chair here for the IEEE EMC Society in Southeastern Michigan, and I welcome all of you. And I also welcome those from the other chapters, Cedar Rapids, Milwaukee, Central Texas, Coastal Los Angeles, Western Michigan, and Twin Cities. So we may have attendees from all those chapters tonight. We did have about 82 people sign up the last time that I looked. Next month's meeting is our EMC Fest. And if you haven't registered yet, it's www.emcfest.org. That's .org. And registration is still open. We have a lot of vendor tables. We're pretty much sold out on the vendor tables, but we do have room for some attendees and the students. So register for that. After this meeting, there's going to be a drawing for 3 Amazon gift cards, a $25, a $50, and a $75. You must be present to win those prizes. We use a random number generator against the roster, and we will keep calling names until we give away all 3 of those prizes. I have to leave here shortly, so Candace Suriano will take over as a moderator, and she will do the drawing, and hopefully she'll stop recording at the end. But if not, once the meeting is shut down, it'll automatically stop, so it's no worries there. Jim Woodyard is our awards chair, and he prepared the following letter. Dear Mark Steffka, on behalf of the IEEE Southeastern Michigan EMC Society, Chapter 8, I wish to express appreciation for your presentation to our chapter on April the 21st, 2022, entitled Antennas and Transmission Lines. The chapter has recognized your professional commitment to the education of our members with a speaker award, which includes a donation in your name to the IEEE EMC Society President's Memorial Scholarship Fund. Your name, topic, presentation, and donation may be viewed on our chapter speaker awards list on our website, which is www.emcsociety.org. And also you'll find a complete list of awards going back to 2012. And I'll be sending you an electronic copy of this letter, Mark, after our meeting.
Thank you. Thank you, Jim. Thank you so much. I'm honored. Thank you.
So tonight's speaker is Mark Steffka. Mark is a professor in the Electrical and Computer Engineering Department at the University of Detroit Mercy, and has been on the faculty of the University of Michigan Dearborn. His university responsibilities include teaching undergraduate, graduate, and professional development courses on electrical and electronic circuit design, electromagnetic compatibility, antennas, and electronic communication systems. He was selected as an IEEE EMC Society Distinguished Lecturer and is the recipient of the IEEE Lawrence G. Cumming Award, the EMC Society's highest distinction. Mark has almost 40 years of industry experience with military, HF, VHF, UHF, secure communications, spacecraft, instrumentation, automotive electrical electronics, and industrial electronics. Professor Steffka holds several patents and is the author and co-author of textbooks and book chapters on EMC, as well as numerous technical and papers presented at IEEE and SAE conferences and symposiums. Mark.
Thank you. Thank you very much. You know, it's amazing that I can have 40 years of experience, considering I look like I'm only 35 years old, right?
There you go.
Yeah. Thank you very much, Scott, for the introduction, and hello to everyone. I appreciate you taking time out of your life to join us, to join me. And Candace and I communicated, I guess, whenever it was the latter part of last year, the first part of this year, talking about when I might have an opportunity to present this topic. And I'm honored to be able to bring this to you this evening. This is one of the topics that I had developed when I was a distinguished lecturer. And what I discovered is that while many of us know some of the mathematics of antennas And as we know, the mathematics can get very involved, very complicated. Sometimes people have not had an opportunity to really kind of take a look at what it means, the mathematics and the physics with regard to the ideal antenna or theoretical antenna. And then, of course, as I tell my students, there's two worlds. There's the ideal world, and then there's the real world. And to my knowledge, you'll find the ideal world in the various textbooks and publications, and and so on, even simulation, modeling simulation. To my knowledge, everyone on this call probably lives in the real world, and there are things about the real world that play into aspects of antennas, as well as we typically want to connect an antenna to a transmitter or to a receiver. We use something called transmission lines. And I've also found out that there is perhaps not a lot of information about transmission lines, what they are, what they aren't. When we talk about some of the characteristics, what do we mean about the real implementation of a transmission line? So I'll talk on that. I'll discuss some of the aspects of antennas as related to EMC testing, and then this world is turning wireless and is wireless before our eyes, and talk a little bit about some of the upcoming things that antennas will be a part of our everyday life. It's okay with me if at any point during our discussion, I really want this to be a discussion. Feel free to raise your hand or electronically raise your hand, or just ask a question, whatever. Raise your hand electronically, or raise it on using the camera, or ask a question using the microphone, because I think that's one of the things that we want to be able to do. Is if you have a question at that time, that moment that I can help with, please let me know. So absolutely feel free. And it's my understanding that I need to plan to finish this at 7 o'clock. And it looks like Scott has already left. Candace, 7 o'clock, is that correct?
Yes.
Okay. All right. Well, that's my goal. So hopefully everyone can see my cover page. And if after this discussion, you have some questions or comments for me, or if you have bits of humor that is hard to believe but is actually funnier than mine, I'd be happy to hear from you. So please feel free to contact me. And let's see if I can. Oh, there we go. So introduction. Again, I'm going to talk about the antenna theory, and I want to talk about some of the practical antenna design techniques. Look at some typical types of real antennas, so that when you're looking at antennas or designing with antennas or doing EMC testing with antennas, that some of the fundamentals about those and characteristics, I'm able to help you with those. And certainly the other thing is, many of us at times have built or designed our own antennas. I know in my gosh, what is it coming up? 50 years, is that right? My 50 years of ham radio life, I've built a number of antennas. Some of those antennas actually worked. I know that's shocking them. But we're going to talk about how to, some of the tools that I have used to design and build antennas. I was in the, as many of you know, I worked in General Motors, worked at General Motors for a number of years, and I was spent a good portion of time in the electromagnetic compatibility group. And after that, I had an opportunity to move to the vehicle antennas group. And it's just amazing time the last couple of years, how complex or how many of our systems are depending on antennas today. So here we go. Since I am in academia full-time now, what would any session of mine be without a pop quiz, right? So I have the first pop quiz here, and I'm moving my mouse on the screen. Can you see the mouse or not? Probably. It's near the word every right now.
Yeah.
You can see it?
Yes, indeed.
Oh, okay. That audio is really low. I'm sorry.
I can hear it. I can see it.
Okay,
You got
wonderful.
it.
Thank
You
you.
got it.
Okay, thank you. Hi, Kimball. Okay, so as we know, every single current must return to its source. And we learned that back in basic circuit analysis. If it doesn't return to its source, that means it's not flowing in a loop. And if it's not flowing in a loop, that means we don't have a circuit at all. So every current must return to its source, and the path of the source and the return current should be determined. You notice I said should be determined. This is where, many of us spend a lot of time in EMC because the current's flowing where someone had never thought it's going to flow. Key concept here. We're going to talk about the source, and we're going to talk about the path of return or the return path. And as many of us have learned over the years, that some people are kind of confused on this one. And of course, we know that current takes the path of least, and some people actually say the word resistance. Then it's actually the least impedance. That's absolutely critical when it comes to understanding the operation of an antenna, because there's sort of a philosophy, or excuse me, there's a discussion out there about something called displacement current and conduction current. We really need to understand current takes the path of least impedance, not least resistance. So in reality, the current flow, again, is by, and this is sort of a debate, conduction or displacement. Typically, we would say that the current flowing in a conductor or on a conductor, I guess that's sort of interchangeable, is a conduction current then. What about a capacitor? What's interesting about a capacitor is, in order to make a capacitor, we have, of course, a conductor and another conductor separated by some type of dielectric. And we learned a dielectric is an insulator. Yet at the same time, we talk about the current flowing through the capacitor. This is where there's a phrase known as displacement. What actually happens is we will charge up, let's say this top plate of the capacitor, we'll put a positive charge, and the electric field now repels positive charges from this lower plate. And we end up with a positive and a negative charge across the capacitor. So I guess, yeah, you can kind of say displacement, there's a thing as conduction current, displacement current, but it's really just, it's a propagation of charge. That's all current is. Well, we know that if we have, let's say, parallel paths for current, that the majority of the current has to take or will take the path of least impedance. And if the current is DC, which by the way is really nothing more than just a special case of AC, the impedance is generally determined by the resistance. If the current's not DC, including pulse DC, the impedance is determined by reactance of the circuit. And the reactance is actually, the reactance can be either capacitive reactance or inductive reactance. And, certainly from an EMC standpoint, many times we're concerned about unanticipated coupling, capacitive coupling or inductive coupling. What's interesting is that the capacitance, there we go. The capacitance is determined by conductor proximity. Again, if we take a conductor and another conductor and change the distance between those two, we change the capacitance. Of course, as we decrease the distance, it's an inverse relationship. Decrease the distance between the two conductors, the capacitance goes up. And significant or most significantly is that the concept of inductance is interesting, because inductance is really nothing more than just an evaluation of the magnetic flux around a conductor divided by the current. So that's why when we have a coil of wire, we generate a large magnetic flux. And that's why we have large inductance, because we generate a large magnetic flux for a certain amount of current. If we take that, let's say, coil of wire and kind of straighten that up, we get rid of the multiple turns, we have a single turn, we still have inductance there because we still generate a magnetic field. However, the magnetic field is significantly less due to, even though we have the same current. So inductance is due to the magnetic field that's created by current. So let's kind of bring in some other aspects when we talk about antenna design. And one of the other aspects, it turns out that antennas antennas, or good antennas, are really a function of what frequency we are operating the antennas on, or what frequency we want to operate those on. And that, of course, is related to the the frequency determines the wavelength. And the design of an antenna is related to the physical physical design of an antenna is related to whatever frequency or whatever wavelength we're concerned about or want to communicate on, or whatever. Another key thing, and this of course is used a lot in EMC, is dB. And of course, dB is used to measure a ratio. Many times we talk about the significance of 3 dB. That's the, plus 3 dB is 2 times the power, minus 3 dB is 1/2 the power. 6 dB, if we say we're going to change a voltage by 6 dB, what's that mean?
Means you're either doubling it or halving it.
Yeah, exactly. And the reason it's different from 3 dB is because when you stop to think of it, and the rules of logarithms are that power is V squared R, or power is I squared R. So that squared term is pulled out in front. So significance of 3 dB would have to do with power. Significance of 6 dB would have to do with voltage, or perhaps a field strength, maybe amps per meter or volts per meter. All right, to start to have a discussion about antennas, we really need to go back and look at the basics of electromagnetic waves. And the thing that is critical is that electromagnetic waves are vectors. And of course, we know a vector has two aspects. It has a magnitude, and it also has a direction. And we go back to looking at the radiated field, let's say from a device, let's say an unintentional radiated field from a device, from a component. We're going to have a relationship between the magnetic field vector and the electric field vector, and those will always be orthogonal to each other. And what we would say is, you can kind of see here that the and let's see if I can do it correctly here. Whatever, you wrap the use your right hand, you wrap the electric field. Oh, this would be so much better in person. Wrap the electric field in the magnetic field, and your thumb would indicate the direction of propagation. This is important because this determines or this impacts us, because antennas have polarization associated with those. And I think many of us have had experiences where we're trying to use our wireless device, and it's we're not receiving a signal or transmitting a signal. Maybe we'll change its direction or change its position. Or the other famous example is, hopefully you can kind of see these, right? You see these? I think, maybe.
Yep.
Rabbit ear.
Rabbit ear.
Yep. Rabbit ear antennas. And rabbit ear antennas are interesting because they were popular back in decades ago then, and they're coming back in popularity now. And I think what many of us are discovering is, by changing the geometric relationship of these two elements of the antenna, we may pick up a signal or not pick up a signal. So that illustrates the fact that the electromagnetic waves are vectors, because the intensity is not changing wherever we're receiving the signal, but the polarization of our antenna with respect to the wave is changing. Generally, the convention is we would talk about something called a monopole and a dipole antenna. And the word dipole means is essentially we have two In the case of electric field antenna, we have two conductors, therefore dipole. And in the case of something called a monopole, we just have one. Here, let me try this. There we go. We just have one. And normally, a monopole antenna, which is we can think is the active part of the antenna, is in a vertical orientation. Okay. All right. So let's look at Maxwell's equations here. And I really, I don't know why I put this here, because I really prefer the integral form of Maxwell's equations. However, we'll use this differential form for now. Really, what Maxwell's equations tell us is that whenever we have a changing electric field, wherever it went someplace here, we generate a changing magnetic field. And whenever we have a changing magnetic field, we generate a changing electric field. And again, this is a key concept when it comes to antennas, because we also have, or when we generate these fields can be affected by the value of the material, of the permeability of the surrounding material, or the permittivity. Then Maxwell's equations form what's known as, this is the wave equation. And we can use these to help us understand the parameters in electromagnetic wave propagation. Let's now look at some of the conventions that we use, and I call this the metrics of electromagnetic waves. And of course, we know electromagnetic waves travel at what's known as the speed of light. Then we would typically express a signal in terms of its frequency, or many times we would also express it in terms of its equivalent wavelength. Then, and I have put on the slide here that we talk about lambda, which is referred to normally as wavelength, and it's just the propagation speed divided by the frequency. So, for example, 1 megahertz, which of course would be 1 times 10 to the 6, if you work through the math, the wavelength comes out to be 300 meters. Then, and as we change the frequency, the wavelength will change. What wavelength means is how far. Was there a question? Okay, what wavelength means is essentially how far the electromagnetic wave has traveled distance in one cycle. So as we increase the frequency, we know the frequency goes up, the period goes down. If the period goes down, the electromagnetic energy cannot travel as far. So as we go higher in frequency, the wavelength decreases. That's a key parameter when it comes to antenna design. Any questions? Okay. Well, why do we have antennas? Can anyone tell me, why do we have an antenna?
To transmit electromagnetic radiation.
That's it, from point A to point B. If we could transmit it from point A to point B without using an antenna, would we? Yes. So that's why we have these things called wires. There's only two ways to transfer energy: wired, or through conductors, or wireless. There are certain advantages to antennas. Normally, you're able to change the physical relationship between a source of energy and a receiver of energy. Well, what's interesting is normally in a wired system, the signal or the power has very, very little attenuation. So we send it from point A to point B, and it's pretty much depending kind of sort of on whatever the value was that we started out. Is the received energy. Different case with regard to antennas. An antenna really just captures a small amount of the energy that was originally transmitted. So what we want to do is we want to understand how antenna performance is based upon physical parameters, and understand how each parameter then can be modified or changed for a specific application. Of course, we can talk about electromagnetic waves in terms of light sources, and it's pretty much when we're talking line of sight propagation, it's pretty much a good analogy. Generally, we know that if an antenna works well as a transmitter, or excuse me, if we're using an antenna to transmit energy, what we want to do is basically send out the maximum amount of electromagnetic energy radiation then as possible. And generally, an antenna that works well on transmitting also generally works well on receiving. There's some kind of impedance matching issues, but by and large, it also works well. So a transmitting antenna, we normally would want to make it maybe physically as large as possible to have a maximum efficiency of coupling energy from the antenna to the air. And generally on the receiving side, we again would probably want to optimize or make the antenna as large as possible to improve our reception. So which brings me to a question. I think some of you have heard this before. Did anyone hear about the two antennas that became married? The ceremony was okay, but the reception was great. All right, everyone must be on mute. I didn't hear laughter over that one. Not even a drum roll on that one then. Okay, so let's, there we go. Okay, I feel better now. Okay, so let's talk about something called antenna regions. And when we talk about antenna, typically we refer to something called the near field and the far field. And the near field region of an antenna is interesting. It generally starts at effectively the physical location or the physical boundary of the antenna and goes out for some distance, perhaps maybe a wavelength or thereabouts. And that's what's known as the near field region. And there's some properties in the near field region that take place. I don't know if you really call it an antenna. When we say antenna, typically what we refer to is we are very, very far away from the antenna, very, very far away from the source of the energy. And the important difference is that in the far field, whatever the energy is being received, let's say by receiving antenna in the far field, it has no impact upon the let's say what the transmitter is sensing in the near field. So near field antenna, I guess maybe it's sort of an antenna. It's really more of a coupling type of phenomena. You can think of perhaps wireless charging. Then I know they use antennas. It's not really an antenna. It's because you're in the near field. So we're going to focus on far field. And far field has some unique properties that, especially when it comes to a certain type of antenna. So we would normally have a transmitter and a receiver of energy, and the location of a receiver in near field again may impact the characteristics of the source. However, a receiver in the far field has no impact upon the source. A radio transmitter sending out FM radio transmitter sending out 100,000 watts in a metropolitan area. It has no idea how many how many radios are receiving that energy. It's just radiating out the energy. It turns out that if we go back to looking at Maxwell's equations and the physics of electromagnetic waves, remember I said we have electric field vector and a magnetic field vector. It turns out that we can look at the ratio between the magnitude of the electric field vector and the magnitude of the magnetic field vector. In the far field, it is known as, of course, the electric field vectors in terms of volts per meter, the magnetic field vectors in terms of amps per meter. We put volts per meter over amps per meter. The meter cancels out. We end up with volts over amps. So we have a unit called ohms. Far field condition is known or far field condition is defined where the characteristic impedance of the electromagnetic wave is 377 ohms. Then, so can anyone tell me why we would care about that? What does that mean for us? If you were going to design an antenna for the to pick up energy in the far field, what kind of antenna would you want? Yeah, Daniel.
I think I'd want an antenna that's matched with the environment into which it's transmitting.
Yeah, you're right. And there's a bunch of different things embedded in that. One of the key things is the magnitude of the magnetic field, magnitude of the electric field is 377 times the magnitude of the magnetic field. That's why most of the antennas that exist are used or use the electric field vector. 377 times the magnitude of the magnetic field vector. There's some other properties associated with that. So that's interesting. So we can have two types of antennas. We can have electric field antennas and magnetic field antennas. It turns out when we're back in the near field, we define that as where the characteristic impedance is not equal to 377 ohms. It's either greater or less. That's a whole nother discussion. Okay. All right. So here we go. Let's talk about the evolution of electric field antenna. I love this. This really goes down to what we talked about, whenever it was, on the first or second slide. An electric field antenna is really nothing more than a conductor and a conductor separated by dielectric. And of course, we may recognize this. This looks like a what? This looks like a
capacitor.
Yeah, it's a capacitor. And what's the purpose of a capacitor? The purpose of a capacitor is to store energy in the form of an electric field. Really, all an electric field antenna is nothing more than we take a conductor and a conductor and we just open it up. Then interesting. Do we still have capacitance here? Absolutely. We have a conductor, we have some kind of dielectric. Do we have a circuit here? Absolutely. Current or charge will flow up, let's say this side, and create whatever will create a charge here, just like a capacitor. And now we will cause essentially displacement current to flow between these two conductors. And how good of an antenna is a capacitor? Terrible. How good of a capacitor is an antenna? Terrible. Right? But what's interesting is the physics of the two are basically the same thing. So this is what's known as a dipole or electric field antenna, and it's just simply an open capacitor. Okay, question on that? All right, so we talked about electric field antennas. Let's talk about magnetic field antennas. We also have these things called magnetic field antennas. And going back to basic physics, how would we typically create a magnetic field? Anyone recall?
A current?
A current, absolutely. Michael, you know that a current flowing in a conductor generates a magnetic field, the right-hand rule, right? So magnetic field antenna is interesting because it is really nothing more, and I just happen to have one here, really nothing more than just a loop then. And a loop is an inductor then. You can kind of think of it as one half of a transformer. And are loop antennas useful? Absolutely. But if you're going to use a loop antenna, which component of the electromagnetic wave will it react to? It'll react to the electric,
The magnetic field.
The magnetic field. And it turns out there are advantages because a lot of times the atmosphere has a lot of noise that essentially is due to electric field sources. So loop antennas operate on magnetic field. Key concept in any type of antenna is the concept of resonance or having a resonant circuit. We'll talk about that in a second here. All right, so some of the other things in antennas is from practical or real antennas, we would talk about antenna gain or pattern. Gain is basically a function of geometry where we get currents flowing on an antenna and they have constructive and destructive interference and create some type of a pattern where it receives or sends out energy in a certain direction. We could talk about something called directivity. And again, this is really a function of the geometry itself. The key aspect in an antenna is its impedance. And you stop to think of, or when we think about an antenna, is really nothing more than a circuit. We know from basic circuit theory, maximum power transfer takes place when we are able to match impedances. In this case, though, an antenna, because it has capacitance and inductance, has something called complex impedance. Then we have something called bandwidth. Bandwidth is really based upon the physical size of the antenna. Generally, a wide bandwidth antenna or works over wide frequency physically is fairly large. Based upon directory, I don't think that's correct. It should be based upon directivity, I think, and impedance characteristics. What's interesting is we would normally talk about the bandwidth for a particular implementation of an antenna. The other thing is efficiency, and the efficiency of an antenna is, again, how efficient we are in converting from, let's say, current that we're putting into an antenna to generate an electromagnetic wave or vice versa. All right, let's talk about antenna pattern. Some of you may be familiar with the fact that there's a concept known as an isotropic point source. And an isotropic point source essentially is an infinitesimally small point, and it radiates energy out in 300, like a sphere then. And it radiates the exact, or the energy it contains, it radiates uniformly around that sphere then. Is that possible? That's in the ideal world. Is that possible in the real world? No.
Nope.
Because, oh, go ahead.
I was just going to say, no, it is not.
Okay, Michael, why is it not possible in the real world?
Because an isotropic, well, trying to build something like that, the antenna would have to be infinitely small, and I don't know how you get an even if you made something really small, how you would get it to radiate, because its impedance would be extremely low, and its efficiency would be like almost nothing.
Exactly. Well, yeah, leads me to the next point. How useful is an isotropic antenna?
It's useful as kind of like a reference source, which is why it's used all the time.
Yes.
You can't build one.
Right. Yeah. It's interesting. So what we would talk about many times is we would compare a real antenna to this theoretical isotropic source. Doesn't seem to make sense 100%, but that's okay. There's a difference here between the ideal world and the real world. And let's take a look at this particular example. What this says is that we have some type of, let's say, a radiation pattern. So we are sending out energy in this direction. If we're transmitting a signal, we're sending out energy kind of in this direction. As you can see, it's non-uniform. If we go and we put a sphere around this whole antenna and do all the integration, we're going to find out we are sending out a certain amount of energy, or a certain amount of energy, but it's non-uniform. That's a good thing. And it's a bad thing. When is a non-uniform characteristic a good thing?
Well, one reason would be like if you want to get instead of having all the energy radiate out in directions that you don't care about, You really, if anything, you want to focus it in the direction you do care about. That's one way to look at it.
Absolutely. And, we use this, when we have fixed locations, we have, buildings with microwave links and so on, or we have geostationary satellites. We would take our dish and point it at that satellite. You don't care about the signal, here on Earth. What you're trying to receive is that signal from, DirecTV or whatever. What's the disadvantage of an antenna pattern?
Well, it's kind of the same thing. The fact that it doesn't, if it's very directive, that means it doesn't pick up in all directions. And there's going to be use cases where you want it to be able to be omnidirectional of sorts, where you want it to be able to pick up in, you don't care what direction a transmitter's coming from. You want to be able to receive from any one of them.
That's right. That's exactly right. Perfect example is, you want to be able to connect to your home Wi-Fi, or you want to be able to connect to a cell tower, cell base station, or so on. So there is a characteristic called antenna pattern. Antenna pattern is really, it's as a result of physical implementation of an antenna. We do talk about antenna patterns in the context of comparing them to isotropic. We actually use something called DBI, small d, large B, small I, and that would refer to effectively how an antenna compares to this isotropic. If we had an isotropic, let's say isotropic antenna located right at this point would have uniform radiation pattern. In this case, though, where is that there? In this case, we would say, well, it looks like it's kind of amplifying the amount of energy or power that's radiating. So we would say we have 3 dB gain, or 8 dB gain, or whatever it has to be. However, you don't get something for nothing, because you move the energy. Let's say you radiate to the lower right here, you're going to lose energy. Let's say heading off in the whatever upper direction there. Okay. We may use it to our advantage. It may be a disadvantage. Key concept, and this is where we really now come down to the thing I really enjoy about antenna physics. There is a value of a physical length of an antenna as a function of wavelength, and that happens to be known as a quarter wavelength antenna. And a quarter wavelength antenna is, just as it sounds, the main portion, or let's say the source of the energy, is physically 1/4 of the wavelength then. So let's go back, if the wavelength again is 20 meters, we would say that a efficient antenna, the physics turns out that the efficient antenna would be 1/4 of 20 meters, or about 5 meters long then. Well, physics actually works in our favor, because as we go higher and higher frequency, especially nowadays with with our wireless systems, we want to send higher and higher rates of data, use wider bandwidth. Wider bandwidth generally means we use higher frequencies. That allows us to have a smaller and smaller quarter wave antenna. So, the example here of whatever the rabbit ears, and if we were doing this live, you would see I'm pulling these out. And so you adjust the length of these ideally to be a quarter wavelength and a quarter wavelength, which makes what's known as a half wave dipole antenna. And that's, again, another one of the standard type of geometries that works really well. This is, for whatever frequency that happens to be. And some of you may recognize this type of device. And this type of device is a wireless router. And I know many of you have wireless routers. What do you note about the physical length of the antenna on this wireless router? Long or short? Short. So that tells you this uses very high frequency. This sort of looks like a dipole arrangement. It's not. It takes advantage of spacing between two monopoles. That's a whole nother discussion. But generally, by and large, you can look at the physical length of an antenna and sort of estimate what frequency it's designed for. Okay. So antennas are conductors, as we said. Conductors have physical dimensions. length, width, area. Because those conductors have physical dimensions, then that now goes back to what we talked about earlier. We have length, we have width, we have separation, we have capacitance. We also have a loop of current. We have current flowing from a source to a return. It says we have a loop. Whenever we have a loop, whenever we have a loop of current, what else do we have to have?
Inductance.
Why? Why do we have to have inductance, Michael?
Well, because you got current flowing and you've got, if it's a loop, that means you've got an associated magnetic field there as well.
Absolutely. Absolutely true. Yep. Here's our dipole antenna. This is the dipole antenna. Let's say we send current up this conductor here. Where does that current go? Well, via displacement current, it couples over to the other conductor. And let's say it heads down here. Is there an electric field? Yes, because this is a capacitor. Is there a magnetic field?
Yes, there is, because you got current flowing in those elements.
Has to be a magnetic field. If there's an electric field, that says we have capacitance. If there's a magnetic field, that says we have to have inductance. We have to have inductance. Now we have capacitance and we have inductance. That should sound familiar. There we go. This is a key concept when it comes to antennas. An antenna is really nothing more than a resonant circuit. Interesting. Interesting. So let's look at the mathematical relationship or the equation for an antenna. Can we talk about the capacitance in the case of an electric field antenna? Absolutely. Capacitance between here. It's difficult to define at times, and there is still capacitance. Can we talk about magnetic field? Absolutely. When is our antenna resonant? Our antenna is resonant when the value of the reactance of the here equals the value of the reactance here. That's all there is to it. Then, so we would represent that as the impedance of the antenna is equal to plus JX minus JX, and at resonance, the magnitude of X is the same, therefore they cancel. So this becomes 0. And then we have something called the radiation resistance. Now, the radiation resistance is interesting. Physicists don't 100% really agree with the concept of radiation resistance. That's okay. Then, but the radiation resistance turns out it's a value that reflects or indicates how well the antenna performs. So let's just do something really, really quick here. I think I have it. Yeah, there we go. So the radiation resistance, it turns out the quarter wave antenna is about 37 ohms. Then this is a monopole. So I might jump back a slide here. So if we were somehow to put 1 amp of current into this antenna, 1 amp of current into this antenna, would power radiate from that antenna if we put 1 amp into this antenna equivalent circuit?
Yes, it would. And because given the radiation resistance you gave of 37 ohms, that means that the radiated electromagnetic power is going to be 37 watts, because it's
exactly.
I squared times R.
That's exactly right. That's exactly right. So that tells us then that antenna is converting current into a radiated power. So here we go. Generally, what happens is when you decrease the physical length of an antenna, the parameters change, and the physical length is what determines the radiation resistance. So a resonant antenna is a really, really good antenna. Well, sometimes you're not able to fit a resonant antenna onto, let's say, a device. This is a 27 megahertz transceiver. And this is a vertical antenna. Looks like a monopole, probably is a monopole then. Can anyone tell me what the wavelength of a 27 megahertz signal is?
It's
3
about
meters.
11 meters.
Yeah, 11 meters. What is 1/4 of 11 meters?
About 2.5 meters, 2.5, 3 meters.
Yeah, which is 3 meters, which is what, about 9 feet. This probably is not a 9-foot antenna. Is my right, Ben?
I don't think so. It wouldn't be handheld.
It wouldn't be handheld at that point. So we can do something interesting. Then we can physically reduce the size of an antenna. Then, as an electric field antenna, we can reduce the size in a really interesting way. Remember, let's go back to the basic antenna circuit. If we physically reduce the size of the antenna, there's something interesting that happens. Is effectively the capacitive aspect starts to take over. Or excuse me, no. If we just reduce the physical size, the capacitive aspect starts to take over. So we do something, we want to increase the inductance. That's what the equation says. If you could see this really, really well, you would see that there are actually turns of wire in here. What that now allows us to do is to create additional inductance to counteract the impact that we have a capacitance that's dominating, and that is known essentially as tuning and antenna. That allows us to maybe utilize an antenna in an application. Otherwise, maybe it'd be too long. Is a shortened antenna, is that a good antenna or a bad antenna?
It's not as efficient as the full one.
Yeah, it's not as efficient. But the question is, what's better, a low efficient antenna or no antenna? Of course, the answer is you'll probably take low efficiency compared to low. Yep. Yeah. Yeah. Thank you for the comment. Michael, you had a comment too?
No, he pretty much said what I was going to say.
Yep, that's fine. Thank you. Thank you. Okay, so here we go. I put this in here. This is known as tuning an antenna. Then an ideal antenna is Z equal to R plus J0. A short one now is where it looks like it has more capacitive reactance than inductive reactance. So all we need to do is add some plus JX. So I guess this is an example of an antenna with radiation resistance and dominant capacitance. All we need to do is add a inductor. And that's the solution. Interesting. Is it efficient? No, we lose some efficiency, but the key is we're able to still use it as an antenna because it looks like a series circuit. Okay. This happens to be in a book by Dr. Clayton Paul in his antennas chapter. And I love this because what this indicates is as the length of an antenna decreases, if you work along this axis, this line indicates, it says resistance. It actually means radiation resistance. So look at what happens. So let's go right here, 0.25 wavelength, which of course is, we said, a quarter wave monopole. Let's reduce the length. Let's go down. Let's make this 0.15. Going down to 0.15, the resistance or the radiation resistance has now gone down to about what value?
10 ohms.
10 ohms. So if we put 1 amp into this antenna, about how much power would we radiate?
10 watts.
10 watts. Good antenna or bad antenna? Well, not a great antenna, but better than no antenna. Okay. And if you're looking for, if any of you are looking for more details in this, I'd be happy to share with you where in Dr. Paul's book this is. But this is a really interesting chart. When I first came across it, I hadn't seen it anywhere else. All right. So here we go. Mobile two-way radios. I love this. I love this. This is like the dream vehicle of anyone who has a ham radio license, right? And you can see that these are antennas with a kind of a large base at the bottom. That base typically holds a coil or holds an inductor. So this antenna is operating on a frequency that would be lower than what its physical size would be. Here's some examples of some recent antennas, obviously for, this happens to be for a automotive application. And we're using all kinds of different type of structures, printed circuit boards, and there's something called a helical antenna. Has some unique properties to it, but it's all the same physics. It has to do with the physical geometry of the conductors themselves and the frequencies that we are using. Here's some examples of antenna structures. I put this in here. You know, does an antenna, the ability to send or receive electromagnetic energy, does it really care what the structure looks like? No, it really doesn't. However, the structure will affect the pattern. And this is a directional antenna, sends energy or receives in that direction. This, may be a vehicle, skin, conductive skin is being used as an antenna structure. Here's an example of someone holding a cell phone. And what's interesting is your hand, your body may actually be the part of the return path of the antenna. All right. So I want to jump into antenna measurements here. And some of the antenna measurements that we would want to be concerned with consist of the gain and the pattern, which we talked about before. We want to know whether we're in the near field or the far field. Here we go. Basic antenna tools. I use these things all the time. A multi-tool and a measuring tape, because one of the fundamental aspects of antenna design is the physical length of the antenna compared to whatever frequency we want to use it on. A key parameter, as we talked about before, is something called the impedance of the antenna. And this happens to be a device I use, an SWR analyzer. But what it does on its display, the display indicates the real portion and the imaginary portion of whatever antenna or load I'm connecting this to. And that helps for me to understand, is the antenna physically too long? Is it physically too short? But another key aspect is by looking at the R, or the radiation resistance value, it tells me how efficient the antenna is. And we kind of talked about this, reduced size antennas. Again, we can have a shortened monopole, shortened dipole. There's slot or patch antennas. If we were in person, I would show you some of the things I love doing on my iPad. And that is, we can actually do antenna simulation. Now, even on handheld devices. This is a simulation I did on my iPad for, okay, there we go. Simulation I did on my iPad for a half-wave dipole, and it shows the dipole length, and it shows R in 7.3 times 10 to the 1. That's the radiation resistance. And then, it also shows the radiated power. This is actually, I think this current here is the peak value. So we're talking power when you talk about RMS, but we can do simulation now, even on these handheld devices. Now, again, here's an example of a shortened dipole. So I physically went from 0.5 wavelength to 0.15. And for the same, for whatever that current value is, you can see that the radiated power went from whatever that was here, about 36 watts or 37 watts, as as you see here, to about 0.5 watts. Interesting. Okay.
Quick question is, and the radiation pattern, is that showing directivity or gain? Because in theory, the gain should have dropped.
Well, yeah, it depends on how you characterize it, right?
But if it's showing directivity, it'll match exactly. This will be the same.
Yeah. I think this is I don't know, Michael. What's it look like? Is it showing? Is this directivity? I don't think it's showing. Well, let's see. Okay, here's directivity. So this is 2.2 dB. It's obviously 2.2 dBi. Here is directivity at 1.7 or 1.8.
Oh, that's actually gain then.
Yeah, thank you. That's a good point. Thank you.
The one thing that really what directivity is it's nothing more than, or gain is directivity times the efficiency. So in this case, as you shorten up the antenna, the efficiency is going to drop, and therefore the gain's going to drop, but the directivity stays the same. But so if the directivity is like in, or if you do it in dBs, if the directivity is in dBi, you can directly add you can determine the gain by taking and adding the directivity in dBi with the efficiency, but the efficiency has to be expressed in dB. So like a 50% efficient antenna would be like a -3 dB efficiency.
Yeah, that's a good point. There's all kinds of things embedded in here. Thank you. Appreciate that. Yep. Okay. All right. So let me jump over to antennas in EMC. And many of you are involved in EMC, and you've seen this kind of antenna. This looks like a what? What's this geometry look like?
It's a loop.
Loop. Where would you use this antenna?
If you're measuring magnetic fields.
This looks like a monopole. Remember, a loop would be magnetic field. A monopole would be electric field then. If you want to measure the magnetic field, you probably want to use a magnetic field antenna. If you want to measure electric field, you probably want to use an electric field antenna. So you're going to see that in EMC. I call this dipoles in EMC testing. Many of us have used dipoles in EMC testing. This is kind of, these are dipoles that are for a fixed frequency. This is something known as a biconical antenna. It's supposed to kind of approximate parallel dipoles of different lengths, sort of, which makes it a very broadband antenna. It means you don't have to change the antenna every time you're measuring a different frequency. Here's an example of gain antennas. And again, this provides, going back to what we talked about a few minutes ago, some directionality and some directivity if you want to measure a signal or energy in a certain direction. All right. I put this in here. This is something known as antenna factor then. And antenna factor is kind of unique sort of to EMC people. It describes how efficient an antenna is in converting an incoming electromagnetic wave to a voltage. Basically, you want a low antenna factor, which means it's if you look at the equation, it's the best antenna converting the incoming electromagnetic wave to an antenna voltage. You want it low and as flat as possible. All right, last topic, and I have just a few minutes here. How do we connect antennas to our transmitters or our receivers? We use something called a transmission line. And let's talk about this. A transmission line is really nothing more than a conductor and a conductor. We go from a source to a load, let's say from a transmitter to an antenna. A conductor and a conductor separated by what? Dielectric or an insulator. What's a conductor and a conductor? What's another way to think of those?
Capacitor.
Capacitor, that's right. So you have capacitor, you have capacitance. And we know if we send current, let's say out this direction, it will couple through the inductance and the capacitance equivalents of the antenna and come back in this direction. That means we have a loop of current. If we have a loop of current, what else do we have to have going on here? A loop of current creates a magnetic field. So here we go. This essentially is what a transmission line is. It is just it is two conductors separated by a dielectric. And we characterize the property of a transmission line in the following way. We talk about effectively the capacitance for, let's say, some amount of transmission line divided by the inductance for that portion of a transmission line in a loop. You may be familiar with either coaxial cable transmission line or twin lead or what's called open wire. All those they just have different geometric configurations. What's interesting here is generally the distance from here, the distance from here to here is larger than the distance from this center conductor to the braid. If it's larger, that means the capacitance is lower. And then there is an equation that we use. An equation that refers to the impedance of a transmission line is just simply L, square root of L over C, and it's for a certain amount of length. And if a transmission line is a good transmission line, it has the same geometric proportions. and same geometric proportions means it had, by implication, it has to have the same impedance. That's all a transmission line is. Yeah. Any questions? Okay. I put some numbers on here. The most important point, the impedance of a transmission line, if it's a good transmission line, does not depend on the length of the line. No matter how long or how short that is, the capacitance and the inductance changes accordingly. Therefore, a 50 ohm transmission line is a 50 ohm transmission line, whether it's a foot long, a mile long, 10,000 miles, or 1/2 of inch. It's dependent upon the ratio of the square root of the inductance and the capacitance. There's a little bit of resistive loss. We're going to ignore that momentarily here. Okay. All right. So last couple points. Obviously, the world is becoming more and more dependent upon antennas, and we want to pack more antennas into smaller spaces. It's important for us to understand some of the complexities or some of the impacts of doing that. Can we do it? Can we pack more antennas into smaller spaces? Well, we can. I know some of you here on this evening are doing that kind of work. It's obviously a complex problem because we try to have many antennas for different frequencies to do different things. So sometimes there's coupling and all that stuff going on, but it's all really the same type of physics when it comes right down to it. Essentially, and where I'd like to finish here is the basics of antenna engineering and understanding what a transmission line is really based on analogies to physics and electric circuits. As we see, we can do modeling simulation of antennas that we couldn't do just a few years ago. And that provides us with amazing insight as to what we can expect from our real antennas. But the most important thing is we can still use simple tools. Cut wires a certain lengths because the fundamental parameters or the fundamentals are still there. So with that, sorry, I'm 2 minutes over. Any questions or comments from anyone?
Yeah, quick question. Going back to the 377 characteristic impedance of the atmosphere. Oftentimes antennas are rated like 50 ohms, resonant at 50 ohms, or at some frequency, but the input impedance to the antenna is 50 ohms. How does it go from 50 ohms to 377 ohms for emission into the atmosphere?
Yeah, okay. Yeah, so you're right. And the best way to think of it is in the far field, the characteristic impedance of electromagnetic wave essentially settles out to 377 ohms. What we can do, or it's okay then, obviously many of our systems are 50 ohms. There's a whole set of reasons why that, but our 50 ohm system in a weird way may be actually connected to a 37 ohm antenna or 73 ohm dipole antenna. What happens is after the electromagnetic wave is launched, kind of goes back to the near field and the far field physics, the parameters sort of settle out. Then does that kind of help? Unless anyone else want to comment on that?
Yeah, it's the transition between the near field and the far field, and of course in the near field you have more vector components for the electric field, for example, than you do in the far field, and so that's what has to change, and it changes gradually so that on the antenna itself you have a ratio of E and H to be 50 ohms as far as the transmission line impedance into the antenna, but that goes through this process and changes to far field where you just have a single directional E field and an H field corresponding to orthogonal, and that ratio is 377.
Yep.
Well, an easier way to look at it is you come in with a 50 ohm transmission line defined by the geometry or space between the signal and ground conductor. And then as you enter the antenna space, that space between the ground plane in the antenna lead gradually increases. And as it gradually increases, the impedance gradually increases. So you get to the 377 ohms. So it presents a changing geometry to the face of the wave as it moves into that space. So it's pretty straightforward behavior.
Mm-hmm. Yep. Dan, that was you, right?
Yeah. Hi, Mark.
Yeah. Yeah.
Long
Hi.
time no
Hi.
see.
Gosh, been a long time. Yeah. Good. Thank you. And I think Daniel, that you were asking a question, or that was your question.
That was my question.
Yep.
I relinquished the.
Yep. You okay so far?
Yeah, perfect. Good answers. I like it.
Okay. Thank you. Yeah. Thank you, everyone. Okay. Okay. Anything else? I'll make these slides available then. And Candace, I should send these slides to you. Is that correct?
Yes. And Mark, this has been so much fun. Thank you so much. It's always great to have you.
Well, thank you very much. I appreciate everyone's time then. And again, you have my email contact, anyone, you have my email contact information. If you have questions or comments, please let me know. All righty. With that, Candace, anything else you want to close out with, or it's back to you?
We want to have a drawing. So the drawing is random numbers that Scott got from the random Google number generator. And the first $25 Amazon gift card goes to Ron Fredericks, if he's still on the conversation.
Yeah,
He-
yeah.
You
It
just
looks
made
like
a
you.
comment.
I'm still
Yes.
here.
Okay,
I'm here.
and the next one, it for $50 is to Ann Cruz, if she's still on the line. Ann, are you still on the line? Oh, that's bad. Okay.
Yeah.
The next one, so the $50 one goes to Ron Missier. Is that how I pronounce it?
That's another guy. another-
Yes, yeah, thank you. Yeah.
Oh, okay. And so you get the $50 one. So let me look and see the next. Jamal Sheffield.
Yes, yes, I'm here.
Yes, so you get the $75 gift card.
Thank you.
So, yes, thank you very much. We have all those emails, and so we will be getting in touch with you. And Mark, we can't say thank you enough. Really.
You're welcome. I appreciate everyone's attention this evening. Wonderful to see a number of old friends here, and I look forward to being able to, we can all be back in person sometime.
Okay.
So thank you.
And does anybody want to stay and chat? I can turn off the recording. Where is the recording? I can't. John's got better eyes than I have, so.
Okay.
Yeah, good question. I don't know if we can stop the recording because Scott started it.
Well, I don't know. It will turn off.
Wait. I can do it.
Oh, can you?
Yes.